Conradi Smith. This is lecture 13 of Cellular Biophysics and Modeling, where we'll be talking about the Morris-Lecar phase plane and type 1 and type 2 excitability and oscillations. So recall that the Morris-Lecar model was a simplification of a 3-variable dynamical system for membrane excitability and oscillations in barnacle muscle fiber. It's reduced to 2 dynamical variables using the assumption that the gating variable for the regenerative and inward calcium current is actually instantaneously or very rapidly equilibrating as a function of the voltage. So doing this allows us to eliminate the gating variable equation for M and just plug in this algebraic function for the steady state value of M here in the term representing the inward calcium current. We still have a gating variable for the outward potassium current that's part of this model. Every once in a while, I'll be talking about this parameter phi, and it's simply a way to change the speed of the potassium activation, the speed of the activation of the potassium current. So you can say phi here is going to essentially be the same as changing the time constant here, tau. So if you make phi a very large number, that would be making the potassium current fast. If phi was a small number, the rate of change of W would always be relatively slow and will be in that regime sometimes, but not all the time, as this lecture continues. So remember that an important set of points in the phase plane are referred to as the nuclines. So the W nucline is all the points in the phase plane for which the rate of change of W is 0. And in this case, setting the left-hand side of the equation for the rate of change of W shows that the way you can make this 0 is by having W actually be equal to its steady state value for any given voltage. So when W is at steady state, it will be equal to this steady state activation function for the potassium current. So basically what we're saying is that one of the nuclines is simply going to be a graph of the activation function for the potassium current. And I also want you to notice that this nucline doesn't depend on the applied current. So here it is. Here's W, V. This is our phase plane, and we can sketch out the W nucline. It's equivalent to W infinity as a function of voltage. Anytime you're on this line, the rate of change of W is 0, and that means that we can only cross this nucline in the horizontal direction. Now, the voltage nucline is more complicated. So the voltage nucline would be all the points in the plane for which the rate of change of the voltage is 0. And if you set the left-hand side of the voltage equation to 0, the capacitance ends up not mattering, but you still have quite a bit of number of terms here, all 3 of which are voltage dependent, and then there's the applied current that's actually occurring here as well. So it's hard to see from the equation what this nucline will look like, but it's clear that the voltage nucline will depend on the applied current. And it'll turn out that in the Morris-Lecar model, this voltage nucline will often look like a cubic function. There, the graph. Here is a numerically plotted graph for particular parameters of the Morris-Lecar model. These are the rates, these are the locations in the plane where the rate of change of the voltage is 0, the voltage nucline. And the interpretation here is that depending on the activation state of the potassium current, the membrane can be either monostable, bistable, or monostable again due to the instantaneously activating calcium current. So, for example, if the potassium current gating variable was quite large and all of them were open, then if you look here for that value of W, the steady state voltage is actually relatively hyperpolarized, and there is only one steady state for this value of W, right? But there are values of W here where there are fewer potassium channels open, like 0.2. That would be 20% of the potassium channels open. And in this case, there's 1, 2, 3 different steady state voltages. If you fixed the gating variable W, this would correspond to a stable steady state that was hyperpolarized, another stable steady state that was depolarized, and then a unstable steady state between them. So people sometimes refer to this as the stable, unstable, and stable branches of the voltage nucline. So here, putting both nuclines on the same plane, we can see that they only intersect in one place when the applied current is 0. And these nuclines numerically calculated using a software package called XPP, which is sort of equivalent to p-plane that you've been using. We can see that there is one equilibrium, or there's one fixed point, and it turns out to be stable. And this is a sort of a resting state. The fraction of potassium channels that are open is very low, so there's very few potassium channels open, and the membrane is relatively hyperpolarized here at minus 60 or so millivolts. Now you can numerically or analytically figure out what the rate of change, the sign of the rate of change of each of the dynamic variables in these different quadrants of the phase plane. And the most important thing to notice is that when you, let's say, cross the W nucline, you move from a region where the rate of change of W changes sign. So it sort of makes sense, right? If this is the location of points where the rate of change of W is 0, then on one side you have negative values, and on the other side you have positive values. So if you look here, you see that the rate of change of W is also negative on this side. And if you look down here, you can see the rate of change of W is positive. So basically, if you were above this nucline, the green nucline, you're going to have a rate of change of the gating variable for the potassium current is going to be negative, and that will be moving in this downward direction. But if you're below this W nucline, you'll be moving up towards it. A similar statement can be made about voltage. So the voltage is decreasing in this region and decreasing in this region, whereas it's increasing in this region and increasing in this region. So when you're below the voltage nucline here, the rate of change of voltage is positive, and when you're above the voltage nucline, the rate of change is negative. So you could just sketch these in your notes. This is the general sort of direction of the flow in the phase plane. It's not something that you would know automatically. It's something that you would be able to glean from the direction field that was calculated with software. But note that as you cross the W nucline, the rate of change in the W direction shifts from upwards to downwards. And as you cross the voltage nucline, the rate of change of the voltage shifts from positive to negative. Okay, so the Morris-Lecar model exhibits excitability, and if you start at different membrane potentials, that would be sort of simulating the effect of a really brief pulse of applied current, causing the membrane potential to be a little bit higher than resting values. You see that can lead to just a subthreshold response where the voltage goes right back down to rest, or it can lead to an action potential where you go upwards first and then you hyperpolarize a little bit below rest and then you relax back. So that's um, the action potential in the Morris-Lecar model. The upstroke is due to the activation of calcium channels, and the downstroke is the recovery that's due to the activation of potassium channels, outward current. This is referred to as a graded response or an indistinct threshold because the values that you pick here for an initial condition lead to different sort of sized action potentials with different latencies. You can get a sense of why this is happening if you look in the trajectories in the phase plane. So different values for the initial condition are leading to different sort of paths of return the rest to the steady state. And some of these sort of go to the right first, cross the voltage null line vertically, cross the W null line horizontally, and come back to rest. Others can more immediately go back to this fixed point without moving to the right first. Now, in order to sort of understand these dynamics, you can think about sort of a limiting case where the voltage is fast and the potassium channels are slow relative to the voltage change. So if that were the case, that would be making this parameter phi in the model small. Then what that means is that if you're not on the voltage null line, then the direction field is going to be pointing either to the left or to the right effectively. So you have horizontal flow is always the first thing that happens when you're in this limit where the potassium channels are slow. And that's because if you're off the voltage null line, the rate of change of the voltage is much greater than the rate of change of W, and so you'll be moving effectively in the horizontal direction. Now, whether you move to the right or to the left depends on which region you're in, and this picture that we've drawn here is showing you this limit where the potassium channels are slow, and you can actually see that the threshold that determines whether you have an action potential or not is given by this branch that of the voltage null line that we call the unstable branch, meaning that for a particular value of W, it would correspond to an unstable steady state that was between the two stable steady states for that given value of W. Okay, so this is the explanation for why action potentials are occurring in this model. And this sort of picture can also help us explain oscillations, because one of the observations is that in this model, if you inject the right amount of applied current, this voltage null line lifts up and to the point where the unstable branch here is intersecting the W null line, and there's actually an unstable fixed point here, but then around that is a continuous closed curve solution, which is sometimes referred to as a limit cycle oscillation. It's a type of nonlinear oscillation. This would correspond to repetitive spiking. If you overstimulate, the voltage null line lifts up so far that you end up having a stable steady state again. Now, it can be shown that when this intersection occurs outside of the knees of the voltage null line, the equilibrium has to be stable. And when the equilibrium occurs inside the knees of the voltage null line, the equilibrium can be stable or unstable. That's the general case. So in this case here, since the intersection is outside of the knee, to the right of the knee of the voltage null line, we know it's stable. It's also true that we know this is stable because it's occurring to the left of this knee here. Now, this is a bifurcation diagram of that Morris-Lecar model using the parameters that we've currently had set. And I want to sort of try to connect this picture to the ones that we've seen before. So um, there are three different vertical lines here. Each is corresponding to a different value of the applied current. So we're now thinking of the applied current as our bifurcation parameter. And for a given value of the applied current, we're going to ask, what does the system do? What are the equilibria for that are possible for that value of the applied current? When the applied current was 50, the only equilibrium was this stable equilibrium that was relatively hyperpolarized, and it was occurring at the intersection of those two null lines. Right, that's this one. For the applied current of 150 microamps per centimeter squared, there's an unstable fixed point, and there's also a limit cycle oscillation, which on this graph is plotted as the maximum and the minimum voltage. So that is this picture. That's 150 for the applied current. And then when the applied current is 300, once again, you get only a single stable steady state. That corresponds to this picture. So what's nice about this bifurcation diagram here is that you see that in one sort of one swoop, you sort of see that the stable steady states will be increasing as you increase the applied current, and then at some point you enter this regime where you can get repetitive spiking, and then at a certain point that repetitive spiking stops due to depolarization block. So it's a nice sort of summary plot of everything that can happen. There's one subtlety here that I'd like you to note, which is that when these periodic solutions with the maximum and the minimum voltage are plotted in this way, and they're sort of solid circles, that's indicating that the periodic solution is stable. It's also possible to have periodic solutions that are unstable, and we'll talk about that a little bit more. The type of bifurcation that's giving rise to these oscillations is referred to as a Hopf bifurcation, and we'll say more about that in subsequent slides as well. So now what we're going to do is just see if we can understand this type 2 oscillation in the Morris-Lecar model by separating the time scales again, thinking of voltage as being very fast compared to the activation of the potassium current. And you can see this picture where when the intersection is happening between the two knees here, then you can glean that in this fast-slow limit, where voltage is fast and W is slow, you'll get this particular type of oscillation here that has sort of 4 distinct phases. You can tell like what is going on in each of these phases just by thinking of where you are in the phase plane. So let me see if I can do that for you. If you start on the voltage null line down here, then what's going to happen is you're slowly, let's do this. Those are the 4 phases. This is the voltage as a function of time. So I'm going to describe phase 1, phase 2, phase 3, and phase 4, which correspond to these 4 different pieces of the limit cycle solution here. So what's happening in phase 1, right, is that the voltage is slowly increasing as you run up along this voltage null line, and W is decreasing during this phase. That means potassium channels are actually closing, and since you're closing an outward current, the voltage is going up. At a certain point, you've closed, the voltage has gotten high enough, W's gotten small enough that there is only one steady state voltage, and that's actually a depolarized voltage over here. And so you'll sort of jump off of this knee and quickly move to the right, because the voltage is a fast variable, and end up close to the voltage null line over here. Now what's actually happened during this phase physiologically is that the calcium channels have opened, right? They're inward and they're regenerative, And essentially you depolarize the membrane enough so that they sort of snap open, and the inward currents are causing you to move to this higher voltage. When you're in phase 3, you slowly move in this direction along the voltage null line. That is a gradual increase in W, which is a slow activation of the potassium current. Activating the potassium current is turning on an outward current, which is hyperpolarizing. That's why the voltage is decreasing during this phase. And that'll happen until you get to this knee up here, in which case the inward regenerative calcium current can't sustain this upper steady state anymore, and the calcium channels close rapidly, and you end up moving back to this branch, the hyperpolarized stable branch of the voltage null line. So this is in words my explanation. If you want to go back and think through each of these stages, it's also described in the textbook. Now, when the potassium channels are very slow, it's actually the case that it can be shown that the equilibrium transitions from being stable to unstable precisely at the knees. So what I mean by that is that if the potassium currents are slow, you will actually end up, the steady state will go unstable exactly when the voltage null line lifts high enough so that this knee ends up on the other side, right? So it's unstable now because the intersection is happening between the two knees. Still unstable because the intersection is happening between the two knees. And then still, and now the intersection is happening just to the right of this second knee, and therefore the steady state is stable again. Now, let's, I want to zoom in onto this bifurcation diagram into this one region here for this values of applied current that are around 90 micrograms per centimeter squared, and make a point that we really have a new type of bistability here, because for this particular value of applied current, there's a lot going on. We have a stable steady state, we have an unstable periodic orbit, and we have a stable periodic orbit. So in the if I sort of blow this up, sort of change the scale of the horizontal axis, you can see this maybe a little bit more clearly. So I'm trying to illustrate here how you should think about the stable steady state, the unstable periodic orbit, and the stable periodic orbit. They're in the phase plane. They're sort of oriented in this way, where there's a stable steady state, a stable limit cycle, and between them an unstable limit cycle. Here in the actual Morris-Lecar phase plane is the steady state and the stable limit cycle for the applied current being 90, and this picture is showing the unstable limit cycle that exists between them. So this is really a different type of bistability, because, and you can see that here in this simulation, I have an applied current of 90 micrograms per centimeter squared. I'm going to inject a little depolarizing pulse here, and it's going to cause the membrane to transition from this stable steady state to a periodic oscillation. And then if I time this depolarizing pulse here and kind of give it at the right time, I can cause this oscillation to end. So what's happening in the phase plane looks like this. We're starting at the stable steady state, and if we inject the right amount of applied current, the first pulse gets us over here, and we're beginning our oscillation. We're on the limit cycle now, going around and round. And then the second pulse was timed so that you jump in this direction across the unstable limit cycle, and you end up in a stable spiral solution that goes back to rest. Now, this sort of explanation is important, because what we're going to be able to do is understanding the sorts of flows that are possible for particular values of the applied current are going to give us a lot of information about how the membrane potential could potentially respond to changing values of applied current or changing values of synaptic input. So let's talk a little bit about this Hopf bifurcation. So one type of Hopf bifurcation is referred to as supercritical, and that's when you have a set of stable steady states that go unstable, and then surrounding those steady states, you have limit cycle oscillations that emerge. So this is stable periodic orbits emerging from a set of steady states. We call this supercritical because the way to think about this is start on the stable steady states, move towards the critical value of the applied current. Here it goes unstable, and then you're going to ask the question, well, did the limit cycles occur on the pre-critical or the post-critical side of the bifurcation? Here they're on the post-critical side, so it's referred to as a supercritical Hopf bifurcation. The other way Hopf bifurcations can occur is they look like this, where the stable steady states will go unstable, but bending backwards, you have unstable limit cycles that are emerging from this Hopf bifurcation. So there are two ways that Hopf bifurcations can be set up. This one's called subcritical because as you move from stable to unstable, you see the limit cycles are actually on the pre-critical side. Now, the significance of this is that if you have a supercritical Hopf bifurcation and you're changing the applied current so that you move in this direction through that bifurcation, you can actually see the membrane response, right, beginning to oscillate as you pass through that bifurcation. And what I want you to notice is that because this is a supercritical Hopf bifurcation and the oscillations are emerging with a low amplitude, you actually can see that the oscillations are starting here with a relatively small amplitude, and then that gradually grows as the applied current changes. So this type of picture is essentially being drawn under the assumption that the applied current is slowly increasing, and that's moving you through this bifurcation here. And you can see that it was actually a supercritical Hopf bifurcation that led to these oscillations, because you can see small stable limit cycles here right after you move through. On the other hand, if you had a subcritical Hopf bifurcation, as you increase the applied current, you would end up moving to the right along these stable steady states, and then the steady states would go unstable, and you would immediately, right, be jumping to some other solution. You can't even tell from this bifurcation what that solution would be. In our Morris-Lecar model, there is these periodic solutions sort of fold back over and become stable again, and so the thing that you would end up jumping to was a stable periodic orbit out here. And so you can see that in this picture, where as soon as the oscillations start, they're kind of at full amplitude. And that's an indication that you went through a subcritical Hopf bifurcation. In both cases, though, when you go through the bifurcation point, this sort of slow passage through the bifurcation, you can see evidence that the membrane wants to spike at a particular frequency. Right? In both cases, when this oscillation starts, it's starting at a particular finite frequency. Here's the Morris-Lecar model, and I think that you're gradually changing the applied current to get this oscillation to start. The applied current is subthreshold now, and then all of a sudden it starts spiking, and these oscillations are actually, you can see maybe right here. You can see here that the the voltage is, well, let's see. I have a little bit of trouble of controlling the movie and doing my pointer at the same time. So I will control the movie and then tell you what I'm observing here. So when this oscillation occurs, right, See how that first spike, right? The first time you actually get an oscillation, it's full sized. Now we're getting multiple oscillations. So I didn't really see a very a wide, like a long phase where we had sort of, there's no small oscillation that's persisting here. This is sort of a stable spiral solution, and then we're immediately at this large action potential. So this is actually, this suggests that what's occurring is passage through a subcritical Hopf bifurcation. Okay, now I'm going to pause now, stop the recording, and then we'll start up again.